Today on The Future of Everything, the future of space exploration. 2019 marks the 50th anniversary of the moon landing, when Apollo 11, Neil Armstrong and Buzz Aldrin walked on the moon with their colleague Michael Collins circling the moon in a ship that would take them all home safely. This was actually an amazing achievement, I think we can all agree, and created a template for all of us to kind of think about space exploration. But it was a very specific template with humans in big rockets with a lot of thrust going to the moon, coming back. It was preceded by a frenzied decade of engineering and innovation that had to solve all the problems of spacecraft design, navigation systems, communication systems, life support when humans were involved, and many other aspects. Then there was kind of a relatively quiet period, particularly for human space travel, after the Apollo program. There was, of course, progress. There was Skylab, there were space stations, the shuttle program. Satellites became increasingly important, and especially with the introduction of GPS, the Global Positioning System, navigation was revolutionized. Other nations developed capabilities and collaborations with the U.S. program and with each other. Now, there has been a renaissance of activity, and we're all seeing it in space technologies, especially with the creation of private industry companies that are now actively creating new capabilities. Every now and then, if you go on YouTube, you can see some amazing videos of rockets that not only take off, but then they land standing up on little platforms in the ocean, and all kinds of things like this. And it includes both efforts with humans and without humans. An emerging area for space is the use of multiple miniature vehicles that work together to solve problems. In this model, perhaps small vehicles may fly in a formation that interact with one another in 3 dimensions to make measurements, to communicate. They may be cheaper to install because they may require less thrust to get them up into orbit or out of orbit. They may be more maneuverable and reconfigurable. They may have longer life. Professor Simone D'Amico is a professor of aeronautics and astronautics at Stanford University. Simone, you have written about miniature distributed space systems. How did you come to work on these, and why do you think they have so much promise for the future?
Thank you for having me, and thanks for the very clear introduction. I mean, I could have not done a better job describing what's going on.
You're very kind.
So, I was a very young student doing my master thesis abroad. So from Politecnico di Milano, I was spending 6 months of research period at the German Space Operations Center, southeast of Munich. And there I got exposed to the first mission I worked on, satellite mission. It's called GRACE, the Gravity Recovery and Climate Experiment.
Wait a minute, say that again.
GRACE is an acronym that stands for Gravity Recovery and Climate Experiment.
Okay.
I saw what was possible to achieve using 2 spacecraft flying in formation in low Earth orbit that would have not been possible using a single monolithic spacecraft.
Fascinating.
And for the GRACE mission, that was the recovery of the gravity field and the mass distribution of the Earth and how it changes over time to unprecedented accuracy.
And you needed to have 2 vehicles in order. This was a measurement that was being made.
Right.
And they required 2.
The 2 vehicles build an instrument. It's like a spring, and they oscillate. And this oscillation is driven by the gravity, by the mass that is underneath. For example, you go over a mountain, the mountain will pull more the leading satellite and less the trailing satellite. So they will start, getting farther apart. And then they will start oscillating. And from these oscillations, by tracking the relative motion, we're able to recover the mass distribution of the Earth globally.
Now, that's fascinating. So let me ask a couple of questions. How big were these vehicles?
So, in the case of GRACE, we are speaking about several meters of length. These are truck size, minibuses. Think of a pickup truck.
Pickup truck in space.
Right. Weighing tons,
okay,
costing hundreds of millions of dollars.
So that is a big ticket item, we can agree.
Right. So when I moved to Stanford 6 years ago, I founded my laboratory with a vision. The vision was to enable future miniature distributed space systems, so leveraging the technologies, the methodologies that I have learned in the past, and make it available to the students, leveraging the push for miniaturization of satellites that is happening today, so to democratize the technology.
Yes. So the idea is that that was an inspiring vehicle, but you said to yourself, even as a young scientist, I think we can do that smaller and presumably cheaper and faster. But this idea of democratization, I want to just dive a little bit into that. In what way do you mean that this becomes like a citizen science capability, or do you mean something else by democratization of space exploration?
Yes. So there are a couple of angles you can see at the democratization. One is what you just mentioned. So we see the advent of citizen scientists where data are made available to the public, ready to be processed by people, normal people, to, for example, identify planets or discover things that the team that has developed the technology was not able due to limited resources, for example, or limited time to discover. But when I refer to democratization here, I really refer democratization of the technology. The technology is becoming available to a wider and wider population, and I refer to young people building startups, proposing missions to NASA, Air Force, and other institutions for execution. Thanks to the lower costs, these technologies are accessible. We can change life on Earth and satisfy the desire of knowledge of humans now much more easily than what was possible just 10 or 20 years ago.
And so this is happening now. This is not a future vision. What is the status of the ability of a startup company to get access to space? I really know nothing about. Do they need to apply for a license? I know there are issues of space garbage, and I think there are people who are worried about tracking garbage in space. So what is the reality for a young person who says, I think I can make a product, but it requires to have things up in space, connected or not connected? What is the process to get that going?
Yes, it's complicated. And in fact, the opportunity comes with challenges. You mentioned a few of them. So the very first challenge is to raise enough funds to be able to design and develop a satellite.
Yes.
So that's the very first challenge. Still, we are not speaking with startups which are comparable with computer science startups, where you just need a few computers to do the job, so to say. We have upfront, we need much more money. So that's the first challenge.
So it's still very capital intensive.
Yes, still. Even if the costs have reduced by 2 orders of magnitude by now. So the second challenge is given by the launch. So, this comes with regulations. You need to get licenses. It comes with potential export control issues. However, the space economy is becoming self-sustaining. So there are hundreds of startups around the world that are building small satellite launchers that are dedicated to the business of launching small satellites. So this is becoming also democratized, the rocket industry. The third one is space situational awareness.
I love that phrase, space situational awareness.
Yeah. So that's a discipline per se that is very important today, where what I can say in a few words, we currently live in like the Wild West of space. So there are no regulations, strict regulations and rules to follow when you send the satellites into space. And so we have a problem of space debris.
Yes.
And a code of conduct that we need to enforce so that the space exploration remains sustainable.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Professor Simone D'Amico about the new generation of space exploration. And we've been talking about the democratization, which has gone quite far. But as you just pointed out, there are still challenges in the situational awareness and I guess both defining the code of conduct and then making sure that people obey the code of conduct. So let's go into some of the opportunities here. You've written about many very exciting things, but you started out with a story about two vehicles, but you've also written about swarms. And when I think about a swarm, I think of many more than two. So can you paint for us the picture of what is the vision for swarms and why might they be useful and important?
Yes, when I start my presentations, I usually show a video that I took on while strolling on Half Moon Bay beach with my dad. I was trying to explain what I do as a research at Stanford, and all of a sudden we saw this flock of birds interacting, working together to accomplish an objective that otherwise would not be possible by a single one of those agents. In that case, after a little bit of investigations, we realized that the flock of birds was mimicking the behavior of a larger animal, much larger, 20 meters large, and so forth, to scare off predators. So now, why is this important when we speak about space? Costs are proportional to the mass of the vehicles. So we see miniaturization of satellites. But if you reduce your size, your volume, you also reduce the capability of that satellite. So how do we overcome that limitation? Then we use multiple satellites to basically accomplish the objective that would otherwise require a gigantic spacecraft or not even feasible.
It's in many ways, it's like the idea of parallel computing, where instead of one big supercomputer, we have zillions of littler computers that can do much the same.
Right. And the applications are manifold.
Okay.
We are speaking about three major areas of applications. One is in Earth and planetary science.
Okay.
Second, astronomy and astrophysics. And third, on-orbit servicing and space infrastructure.
So you might need to help me understand how those are different to a non-expert.
Yeah. To a non-expert, if you look at these three domains, think yourself like, flying in space. Now look down, and that's Earth and planetary science. So you look at Earth, or at the planet you are orbiting around. Look up. No, you're looking at the universe, astronomy and astrophysics. Okay, so look instead at eye level, and that's the on-orbit servicing, helping other space assets, prolonging their lifetime, repairing them, building infrastructure.
Okay,
that's it.
That is extremely understandable.
Okay,
thank you. Down, up, and straight. That I get.
And so in my laboratory, I have several projects that are going to be launched in the upcoming years. You see, as a young professor today, I can say I'm going to be launch this technology in space. So that would not have been possible. I mean, just a few years ago.
So this is a sign of the democratization actually occurring.
Yes, and so we have applications in Earth and planetary science that goes from studying the atmosphere, upper layers of the atmosphere, so support climate change studies, and all the way to astronomy, astrophysics, detecting life on planets which are on other star systems, so orbiting distant stars, all the way to on-orbit servicing, so repairing and prolonging the lifetime of other space assets.
And is the swarm work relevant to all of these, or one or two in particular?
Well, what is relevant is the distribution of functionality in what I call a distributed space system. The swarm refers to a special case of a distributed space system where you have many satellites that are prescribed to fly in a confined volume prescribed by the user for an extended period of time.
Like the birds do for...
Yeah. So you can imagine that having all this variety of geometry in the swarm for an extended period of time, you can collect measurements at different spatial resolution, at different time resolution. You can reconfigure the swarm during the mission lifetime. and obtain a very rich set of data that can be used to back out the information you're seeking.
This is the future of everything. I'm Russ Altman. I'm speaking with Dr. Simone D'Amico about these groups of satellites working together. So that suggests to me that you have a very complex control task of giving the instructions to these individual satellites about how to fly. They need to be economical. Presumably they need to not crash into one another. And then, of course, there needs to be very precise timing. If they're making measurements, you need to know exactly when and where they made the measurements so that you can send the data back home. And I guess that raises the issue of communications as well. So is a core part of your work figuring out how to orchestrate all of these satellites, also with a latency in the communication, I would guess.
Exactly. So I have 4 pillars of research. The first pillar is new mission concepts, and the second pillar is the development of new algorithms to meet the requirements posed by these new mission concepts. And you fleshed out, many of them. So autonomy, spacecraft autonomy, is really an enabler for many of these mission concepts. So what we work on are 3 key tasks, which we call guidance, navigation, and control for multiple spacecraft. Guidance is solve the question, where do we go? Control is solve the question, how do I change my trajectory? And navigation is solve the question, how do I localize myself as a spacecraft relative to the other spacecraft and relative to the planet? This requires sophisticated algorithms to be implemented on board the satellites under very tight constraints in terms of computational effort and with guarantees in terms of their functionality. We cannot guess.
Right. And it seems to me that you also need to give them autonomy because of the time it takes to get your instructions from Earth to the satellites. They need to be able, in the meantime, to make decisions that keep themselves safe and functional.
Yes.
This is the future of everything. I'm Russ Altman. More with Professor Simone D'Amico next on Sirius XM. Welcome back to the future of everything. I'm Russ Altman. I'm speaking with Professor Simone D'Amico about space and the next generation of distributed space systems. So one thing that just we kind of referred to a little bit in the last segment, but I wanted to you talked about codes of conduct. Is there actually a way to be aware of and prevent companies that are somewhat rogue from putting in satellites that are doing things that could be deleterious? They could be interfering with other satellites or represent hazards in other ways, or is that still a future state we'd like to be in?
Very good question. This is a challenging topic and very hot today. So there are no direct ways of enforcing good behavior, if we are able to define a good behavior of satellite companies. There have been a case, for example, of a satellite company launching a few small satellites without permission. Because they were too small. If something is too small, it's very difficult to track from the ground.
And so you have a problem of a rogue object that could cause a lot of damage and it's not trackable.
Yes. And the company neglected that, so it didn't get a license, but anyway launched those satellites. So what could, the government do? Fines, or the government could prevent that company to launch a satellite the next time. But the challenge is really how to track and understand the behavior of. We're speaking about 1 million objects, which are in orbit about the Earth right now, out of which only 3,000 about are operational, are active operational satellites.
Whoa.
The rest is debris.
So this is a huge problem. So the answer is we have primitive mechanisms to control and detect these problems. And if things go wrong, this allows me to segue into the next question, then you might do damage to satellites, or even if you don't do damage, they only have a finite lifetime. So I know that one of the areas you're doing a lot of work in is whether the swarms and the distributed systems can work on the maintenance or repair or the prolongation of the life of existing satellites that are functional. Tell me about that problem. I don't think people think about satellite lifetime as a problem, and then tell me what the potential solutions might be.
Yes. The main reason why the lifetime of a satellite is limited is due to propellant consumption. So think of satellites that are in a geostationary orbit that are used for TV communication. And, Sirius XM, I think it's using satellites in elliptical orbit. So in order to keep that orbit, you need to use propellant. In the geostationary orbit, this is a very valuable asset. A company is asked to keep its satellite in a prescribed box. Yes. Otherwise, you would interfere with satellites that are on the same orbit. Now, the typical lifetime of a standard asset in geostationary orbit is about 10 years.
And this is literally because that's the amount of fuel
Yes.
that it has to keep itself in orbit.
Right. So what do you do when you approach the end of your lifetime? So the code of conduct is to raise the altitude of the satellite to about 300 kilometers above the geostationary orbit. It's a graveyard orbit where all these relict, these dead satellites,
Oh my goodness, what an image.
even if they are fully functional, just because they are out of propellant, they are retired over there.
So you save a little bit of propellant for the final burn, which gets you into the graveyard.
Yes.
And there's this amazing, it's a very fun to imagine, a graveyard of on the order of 1 million, if they've all done this.
Well,
Maybe not.
when I said 1 million objects, I was speaking about objects that go from the size of a centimeter all the way to several meters.
Okay.
It's all the population of space debris.
Yes.
Now, for these satellites, these are very big. These are track-size satellites. And so there is, if you think about the cost of these satellites, like $300 million to provide, satellite TV communication, you can easily imagine a business case where you say, well, I can get closer to you, I give you the propellant, I can attach to you and take over control, and then prolong your lifetime by, for example, 5 years.
It's like a mid-air refueling.
Yes. And there are several companies today that are trying to do that. And in my case, the research is about how to do the guidance, navigation, and control I was speaking about earlier. How can we do it autonomously, accurately, without putting at risk the asset that you will want to service?
Right, because not matching the speed or coming in too hot, as they say, could be extremely damaging and not worth the effort. Is this the kind of thing that you and your group would do with multiple smaller vehicles, or is that not the approach in the case of the refueling?
So we start with one vehicle. This is still a distributed space system because you have two spacecraft that are interacting to accomplish an objective. Now, one of the spacecraft can be cooperative or non-cooperative. The future sees flocks of these satellites that can be used for inspection and recovering the 3D model of the piece of debris.
So now I'm imagining like a hummingbird or a bee that's flying around it, doing inspections, and then if it sees a screw loose or whatever, it makes an...
Right. And even the mothership spacecraft can deploy these very small satellites called CubeSats, for example. These are the size of a shoebox that can be used to do inspection, eventually repair, and then get back to the mothership spacecraft.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Professor Simone D'Amico, and now we're talking about this fascinating idea of prolonging the life through a system of smaller satellites that help us inspect, intervene, and fix and prolong the life of satellites, which otherwise are a third of $1 billion and very expensive. So in addition to these activities, I know that you're looking at life on other planets. I think you mentioned it briefly in the first segment. That always gets people excited. Why? Not why are we looking. I can understand why people are interested in knowing about life on other planets, but what is the special insight that your team might have about how to do this?
Right. There is a key challenge when you want to directly image a so-called exoplanet, a planet orbiting a star that is not our sun.
Yes.
The planets are very dim, 10 orders of magnitude dimmer than their host stars. So you need to block the light from the star, similar to what you will do if you want to see an object close to the sun, using your thumb, for example.
Block the sun.
Yeah. Block the light from the star and allows a telescope to see what's orbiting around the star. This is a formation of two satellites that you can deploy even in Earth orbit, small satellites, where one is the shield.
Thumb.
It's the thumb. Yeah. One of the spacecraft is the shield. The other spacecraft is the eye. They get aligned with the target of interest so that the telescope can see what's orbiting around the star, get real direct images of the planets, and then, thanks to these images, do spectroscopy and detect signs of biological activities in the atmospheres of these planets.
I think everybody who has a cell phone that's been messed up by the sun shining into the cell phone, and you need to shield it so it can take the picture that you're interested in. You're doing this up in space. So in the final last minute, you're teaching a fantastic sounding class. I looked it up this morning. It's called How to Design a Space Mission from Concept to Execution. And I believe, is it for undergrads or graduate students?
Freshmen, first year, first quarter.
Okay, so tell me, what is this class all about, and how is it going, and how are the students responding?
So this class is intended to expose the students to the mentality and problem-solving strategy of a space system engineer. How do we realize complex systems? Now, they are so young, fresh from high school, they don't even know what a spacecraft is. But by the end of the class, in about 3 months, they design their space mission concept, they conceive their own idea, and then they pitch it and present it to a review board from NASA. Now,
so these are real people. They're presenting to real space scientists, not only yourself.
Right. And obviously, I cannot make in 3 months a space system engineer. This is a lifetime achievement. But I can expose them to the mentality. How do you approach a very complex system? How do you tackle it? And I see today many professionals, even senior, that they don't know how to approach a problem in a systematic manner. And that's what I'm trying to convey and teach to these very young students. This obviously links to the idea of space democratization. So after this, the students can get the motivation to create their own startup and realize their own ideas to improve life on Earth.
I would guess that they come up with some crazy, interesting ideas. Can you share any?
Yes. For example, one team is developing a satellite to track plastic and aggregation of plastic in our oceans. That is a very big problem today.
By looking down at the oceans.
By looking down. Another team instead is looking at special techniques, atom interferometry, to recover the gravity of a planet more accurately, and so forth. So many different ideas.
This gives us hope for the future of space as we democratize it and bring it to the young people. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime, on demand, with the SiriusXM app.